Hello, everyone. My name is Sam. I'm here to solve this question. It's all about testing the unbiasedness of an estimator. And we know that under the OLS that the expected value of the sample estimate must be equal to the population. So here we have, suppose the true population relationship is y high, that is high from 1 to n, b equals to b1 plus b2 times xi plus u high. You wish to estimate beta 2 with the estimator b2 tilde equals yn minus yi all over xn minus xn. So where your yn, xn are the last and y1, x1 are the first observation in the sample xi, y high, so y is 1, I is up to 1 to n here. Now, the first question says, suppose that the expected value of ui condition on x equals to 0 for all I, where x is x1 up to xn is the estimator b tilde 2 unbiased. So basically, is this guy unbiased? So that's what the question is asking us now. Is this guy unbiased? Then the assumption is changed in the second one now. Now suppose that expected value of u high given xi, not given x star, it's given xi. That is each of this xi, each one I from 1 to n now, as each of them a condition on u1, condition on x1 is equal to 1, u2, condition on x2 equals to 1. So like that for I. So is the estimator b tilde 2 unbiased? Then the last question, this third question says derive the sampling variance of beta 2 tilde, assuming that ui given x is equal to this, then u high square given x equals to sigma square for all I, and the covariance of ui and xi equals to 0 for all I not equal to j. Then the last question asks us to prove that the OLS estimate of B2 is more efficient. That means when it's efficient, it has lower variance than beta 2 tilde. So now we know that the sampling variance of the OLS is given this, given at this, right? So now let's solve this. So the first question, let me share my board with you. The first question. So from the first question, we know our yi. Yeah, we know our y high to be this. Then we need to prove that this guy is unbiased. So what do we do? So we substitute our yn from here down into this yn. We substitute for our y1 from here into this. Then we break this down, and they will take the expected value of this to find out whether it is actually equals to beta 2 or not. So we have yn equals b1 plus b2 xn plus un Then we know, then we have our y1 equal to what? b1 plus b2 x1. Now, because it's y1 plus u1. So now we can substitute these guys into yn and yi here. So when you do that, you have beta 2 tilde equals b1 plus b2 xn plus un right, minus b1 plus b2 x1 plus u1. So basically, we just so all over xn now, xn minus x1. So from here, if you open the brackets, and this b1 cancel this b1, this b2 cancel this b2, we are left with now if I factorize this b2 out and this b2 out, we have b2 xn minus x1, right, plus un minus u1 all over xn minus x1, right? So now if you split it, divide this by this, you have b2 plus un minus u1 all over xn minus x1. So with this now, I can take the expected value of this now. So I have this. So this is beta 2 tilde. Now let me take the expected value of this. I have expected value of beta 2 tilde. So I'll have expected value of everything here. Beta 2 plus un minus u1 all over xn minus x1. So basically, I take the expected value of all this, everything here. So that gives us expected value of beta 2 tilde given x. Now, because of the assumption, so it's conditional on x because of this assumption. Because of this assumption, UI is conditional on x. Suppose that this is equal to this condition on x equal to 0. So it's condition on x b3 equals. Now, if you take the expected value of from the first page now, if I take the expected value of this, right? It gave me this back, right? So I have beta 2 back. And if I take the expected value of all of those equations that I have this guy, expected value of this guy, everything here. So expected value of UN given X. So this is given X. Expected value of UN given X will be equal to 0. So value of U1 given X will be equal to 0. So that gives 1 over xn minus x1 expected value of UN given X minus expected value of U1 given X. So now, because the expected value of, from the assumption, the value of UI given X is equal to 0. So this is UN becomes 0, this becomes 0. So I have expected value of beta 2 tilde, beta 2 tilde now given X given X becomes B2 plus 1 over xn minus x1. So this becomes 0 minus 0, right? So everything here becomes 0. That gives us beta 2. So it shows that the estimator is actually unbiased. Yeah, the estimator is unbiased. So it shows that the estimator is unbiased. So basically, we substitute for the y. So let's go to the second question now. What was the second question? The second question asks us, and now suppose that the assumption has been changed, that this given 0 for all I is the estimator beta 2 tilde still unbiased. Now we've changed the assumption now to individual expected value of UI given xi now. So individual error given the x. So the second one, so now the assumption has been changed to UI given xi. Now this is equal to 0. This guy is no longer equal to 0. So that's where the assumption changed now. So is beta t is the expected value of beta 2 tilde. Is this still unbiased? Is this guy still unbiased if we change this assumption, right? So let's check that out. So now, from what we did from the beginning, so basically, we solve our y high, look for the yn, put it in here for the yn minus y1 all over xn minus x1. So this is our yn now from here. This is our y1 from here all over this. So you open the bracket and break that down. And that gives us this. Then take the expected value given x. Now this is given given x. So but now we are changing it to giving xi to this given x. So now this is our new assumption now. So what's going to happen there is that we are going to have beta 2 plus 1 over xn minus x1. So the expected value of un given x minus the expected value of u1 given x, right? Now, because this guy is 0, and this is no longer equal to 0, yeah? You see? It's no longer equal to, so we can, this can no longer go to 0. This can no longer go to 0. So we are going to be left with what? That the expected value of beta 2 theta is the whole of this guy. So that shows us that once the assumption change, that if this is equal to 0, this is no longer equal to 0 again. So the expected value of beta 2 tilde given x is not what? Equal to beta 2 again. So now let's look at the third question now. Let's look at the third question. Let's look at the third question. The third question says, derive the sampling variance of beta 2 theta, assuming that the expected value of the error I given x is equal to 0. That's the first assumption now. And the expected value of ui given x equals to sigma square for all I, and the covariance of uj equals to 0 for all I not equal to j. So we are deriving the sampling variance of this guy now. So let's derive the sampling variance. So we have the variance of beta 2 tilde given x equal to the variance of un minus u1 all over xn minus x1 given x, right? So now, what is the variance of ui, for instance? You know that the variance of ui given x is equal to what? Expected value of ui square given x minus expected value of ui given x all square. Now this is this. You know that this is equal to sigma square, right? So we know this. So if this is equal to sigma square, then the variance of un now, so it's constant for all I 1 to n. So it's going to be the variance of it's going to be sigma square plus sigma square minus 2 covariance un and u1, right? Because this is the variance of just variance of this guy alone, not of this guy now. So we are going to have, so this guy is going to become, we know this is the formula for variance that we know this. So this now is going to become what? It's going to become sigma square plus sigma square minus 2 covariance un comma u1, right, all over xn minus x1, right? Now, because I'm taking the variance of this now. Now, this, the variance is focused on this, right? So this guy is seen as a constant, right? Now, if you take this out of the variance sign, you have square. So when a constant comes out of the variance sign, understand? So a constant times the variable. So the constant becomes square. So you take variance, the variance of the variable. Right. So this is un. So this is un. This is and this xn itself is an equation, right? This x1 squared, yeah. So since it is conditioned on x now, this guy is conditioned on x, not xn or x1, right? So it's conditioned on x. It's not conditioned on this xn, right? It's not conditioned on x1. It's conditioned on x. To this guy becomes square, right? So it's seen as a constant because it's conditioned on x. It's not conditioned on xi. So it's seen as a constant, so it becomes square, right? Now, if you add this together, then we know that this guy will go to 0. Minus 2 covariance u, and that's 0. So we are going to have 2 sigma square all over xn minus x1 all square. So that's the variance. So we've calculated the variance for the estimator. Now, let's check the other question. So the last question there says prove that the OLS beta is more efficient. That means it has lower variance than the beta 2 theta. Then considering that our sampling variance of the OLS, right, that's beta 2 OLS is this. It's this guy. So now I'm going to prove, I'm going to check the two, we're going to compare this guy and the variance that we just derived now, the variance of this guy versus the variance of this guy. So which of the two variances is less, right? So we have the variance of beta hat, that is the OLS, beta 2, giving x, beta 2, yeah, giving x, that's beta 2, giving x now. We know that this variance is what? Sigma square all over summation I equals to 1 up to n xi minus the mean of square, right? Then we know that the variance, so the variance that we just prove, the variance is, right? So the variance of beta 2 tilde, that's the last one we just proved. We know that to be 2 sigma square over xn minus x1 square. So which of these variance is more efficient? So we are proving that this guy this is more efficient than this. That is, this variance is less. So we have, let's say we have we have 2 sigma square over xn minus x1 all square. It's proved that it's less than let me see the question again. So we are asked to prove that the OLS estimator B2 is more efficient. Okay, we are proving that the OLS estimator is more efficient. So this is the OLS estimator. So that this guy n I equals to 1 I minus x bar square, right? Prove that this is less than 2 sigma square xn minus x1 all square. So now, if we cross multiply from here, the whole of this will multiply this, the whole of this will multiply this. So we're going to have sigma 2 xn minus x1 square, right? Less than 2 sigma square summation I equals to 1 and xi minus xn all square. Now, this sigma cancel out this sigma. We are left with xn minus x1 square less than 2 summation n I from 1 to n xi minus x bar all square. So now we need to prove that this holds. How do we prove that? Now, this guy is from I1 to n, right? Summation, yeah. So this is I 1 to n. So we can split this guy into 3. Can split this guy into 3. Can transfer this guy down here, for instance. If you transfer this guy in here, you have that these two summation I from 1 to n xi minus x bar 2 is greater. No, if you transfer this guy in here, you have minus xn x1 squared that is greater than 0. So we need to prove that this holds. So how do we prove that? So the first thing is to look at this guy and break this guy down. You can break this guy down, take away the first element from here, take away the last element from here. So take away the last element from here. So I have if I take the first element from here, I'm going to have 2x x1 minus x bar square, right? Now this is the first element of this guy here. This is the first element. Now plus 2 summation. So our high will not be starting from 1 again. It's going to be starting from 2 because we've taken the first element away. So we have I equals 2, right? Then we can also take away the last element there. So if you take away the last element, it will not end in n. It's going to end in n minus 1. So I'm just going to write the last element here. So I'm having xi minus x bar square, right? Plus the last element, which is 2. So the last element here that I've taken away here will be what? Xn minus x bar square. Now minus this xn minus x1 square, all greater than 0. So basically we've seen, so what we are actually want to prove now for the OLSM variance to be efficient, and in this case now at least, you have to prove that this is greater than 0, right? So from here, you can see that this is already greater than 0 because this will always be positive. So we've proven that, right? Proving this. So let me just take away this so that I can have space to undo this, this, and this. So if I take this guy away now, I'm going to have so just note this guy. Let me try to create space. Yeah, I can't create any longer. I can't create any space again. So just note now that this guy is greater than 0. So we have this is proving beyond doubt that this is more than 0, right? So let's take away this now so that we can deal with this. We can deal with this first term, this third term, and this fourth term. You have to prove that all of them are greater than 0. So and I have my what? 2 have my 2 x1 minus x bar square plus 2 xn minus x bar square minus xn minus x1 square greater than 0. So now we can expand this xn minus, we can expand this guy, right? Let's take out this guy and expand this guy. If I expand this guy, I have xn minus x if I expand this, I have xn minus x bar minus x1 minus x bar all square. So basically, I just expanded this. Okay? To be this, right? So now I can substitute this, the whole of this for this guy. The whole of it, because I expanded this guy, and I can substitute the whole of this for this guy. So I have 2x1 minus xn squared plus 2xn minus x bar squared minus everything here. So we have xn minus x bar minus x1 minus x bar square. So basically, if I now open up this bracket, I'm going to have a very long equation. That would be 2x1 minus x bar all square plus 2xn minus x bar square. That's this. Then this guy is going to give me x1 minus x bar square plus 2xn minus x bar times x1 minus x bar minus xn minus x bar square. So that's what if you open up this is what it's going to give me. Now compare this guy now, xn minus x bar. So that means this minus this, I'm going to have only one of this. Also look at this, x1 minus x bar. Then I have this guy again, x1. So we have x1 here, we have x1 here. So this and this and this are the same. So I can subtract this 2 minus 1, that gives me 1. 2 minus 1, that gives me 1. So now I'm left with x1 minus x bar square plus xn minus x bar, right? That is one of this because so plus the whole of this guy 2xn minus x bar x1 minus x bar, right? So now look at this equation. This is x1 minus x bar square xn minus x bar square plus 2, right? So basically this is more like saying you have a plus b all square, right? A plus b all square. So if I collapse this equation together now, I'm going to have, if I collapse, just watch this equation. If you collapse together, like when you have like a plus b all square, right? So when you both, if it has expanded, it has been expanded. But if you contract it, collapse it down, so you are going to have x1 minus x bar plus xn minus x bar, right? all square. So it's very easy to see now that this will go to 0. It goes to 0. So this confirm. So this now confirm for us now. It confirms that the variance of the beta, the OLS beta now, given x, is actually less than the variance of the beta 2 theta given x. So now this is proved. So basically from the beginning, we proved that beta 2 theta is unbiased. So beta 2 theta is this guy. Beta 2 theta is this guy. We proved that this is unbiased. Then we generated the variance for this guy. After generating the variance, so we now prove that the variance of the OLS is more efficient than the variance of this guy. So this estimator, which is beta 2 theta, we check that the OLS the variance, the OLS estimator is more efficient. So if you want to check that an estimator is more efficient than the other, you check the size of the variance. So if the variance is less, so it's more efficient, right? So that's basically what we did. There. So I think it's actually straightforward. So that's it. If you have any question, send to the comment, ask any question you have. So I want to end it here. If you have any question, send to chat. Any question, comment, and consider subscribing to this channel so that you can have more solutions to several econometrics problem that you might have. Thanks for staying with me up to this time. Have a nice day.